Recent studies have made significant progress in developing large language models, or LLMs, specifically for the medical domain. These models can answer expert-level questions and help clinicians in real-world scenarios. Researchers have also highlighted the importance of combining different types of data, like images and text, to better understand complex medical situations, which often involve multiple aspects. In this study, the team introduces a new model called ChatEXAONEPath, designed as an expert-level multimodal large language model for histopathology. Histopathology involves examining tissue samples under a microscope to diagnose diseases like cancer. The model uses whole slide images, which are high-resolution digital scans of entire tissue slides, allowing for a more comprehensive analysis than just small patches. The researchers point out that while previous studies have shown multimodal LLMs can answer questions based on histopathology images, they often fall short because they rely on limited patch-level data from public datasets. This means they don't fully capture the broader clinical context. To address this, the team developed a model that works at the whole slide image level, improving scalability and real-world applicability. They created a retrieval-based data generation pipeline using 10,094 pairs of whole slide images and their corresponding histopathology reports from the Cancer Genome Atlas, or TCGA, a large public database. This pipeline helps generate training data by matching images with detailed reports, enabling the model to learn from both visual and textual information. For evaluation, the researchers designed an AI-based protocol to assess how well the model understands medical contexts from multimodal inputs. They compared the model's generated answers to the original histopathology reports to measure accuracy. In tests, ChatEXAONEPath demonstrated the ability to diagnose cancer from given images, with an acceptance rate of 62.9% across 1,134 pairs of images and reports. This means that in about 63 out of 100 cases, experts or the evaluation system agreed with the model's diagnoses. The model is capable of handling whole slide images from various cancer types, making it versatile for pan-cancer applications. The team argues that this approach allows the model to comprehensively understand the complex morphology, or structural features, of these images, which is crucial for accurate cancer diagnosis. Now, let's delve deeper into the introduction of the paper. Understanding and interpreting histopathology images is essential for cancer diagnosis, but it's a challenging and time-consuming task. These images are intricate, requiring pathologists to undergo extensive training to grasp the medical contexts. Even after becoming specialists, pathologists must stay updated with evolving guidelines due to new discoveries, like biomarkers or emerging cancer types. The rise of digital pathology has led to computational methods for automated diagnosis, with deep learning playing a key role. Deep learning models can detect complex patterns in images, but they often operate in isolation, lacking interaction with clinicians. This limits their usefulness because they don't provide interpretable results or reasoning, making it hard for doctors to trust or build upon them. To bridge this gap, the researchers emphasize the need for interactive computational tools that integrate with LLMs. Large language models are based on transformer architectures, which excel in natural language processing. They allow machines to understand, generate, and respond to human language accurately, thanks to their training on vast datasets, self-attention mechanisms, and ability to handle context. In the medical field, LLMs have transformed how we interpret complex data, including histopathology reports. They outperform older NLP models because of their extensive training, fine-tuning capabilities, and efficient processing. Studies have shown that LLMs can interpret medical contexts and provide expert-level answers in histopathology. However, standard LLMs are limited to textual data and can't directly process non-textual information like images. Medicine is inherently multimodal, involving visuals, text, and other data that aren't always in human language. This is where multimodal LLMs, like ChatEXAONEPath, come in, by integrating visual and textual modalities for a fuller picture. The paper explains that their model uses a combination of techniques to process whole slide images. By leveraging retrieval methods, it pulls relevant information from the TCGA dataset to generate responses that mimic expert reasoning. This involves not just identifying features in the images but also contextualizing them with clinical reports. In terms of results, the 62.9% acceptance rate is a key metric, indicating that the model can reliably assist in diagnosis across different cancer types. For instance, it might analyze a slide for breast cancer and provide a detailed description of cellular abnormalities, cross-referenced with textual data from reports. The researchers highlight the potential of this model to support clinicians by offering comprehensive insights into tissue morphology. This could reduce diagnostic errors, speed up processes, and handle the growing volume of digital pathology data. Finally, the paper touches on the broader implications. As LLMs continue to evolve, integrating them with visual data in histopathology could lead to more interactive and assistive tools. However, challenges remain, such as ensuring the model's accuracy, addressing biases in training data, and maintaining ethical standards in clinical applications. Overall, ChatEXAONEPath represents a step forward in making AI a practical partner for pathologists in cancer diagnosis.